And what I want to talk about today is actually an emerging area in algorithm design that's where we're trying to develop algorithms to handle huge amounts of data that we're facing today. And that's one approach on how to do it. So really, if you think about the textbook algorithms that we see, that we study, they all have the same flavor. That we take our inputs, we read it, we process it somehow, and then we find a solution. And somehow most of the research has been focused on how we process information. But somehow the problem that we're facing today, or one of them, is that we have too much information. So instead of having a small amount of input, we have a huge input. And even just reading it takes too long. So we somehow want to get an answer without even looking at the entire input. And that's the notion of what I call local algorithms. So we want somehow to understand something interesting about our problem without even looking at all of it, just looking at a small part of it and still being able to deduce some global structures that it has, some properties it has. And while we do that, then we need to sacrifice some other stuff. So we might not get an exact answer, we might get an approximate answer, we might need to use some randomness and get the answer only with high probability. But those are prices that we're willing to pay in order to get the answer quickly, even though we have a huge amount of data to process. So really, if you think about it, there's nothing new about this approach. So people in statistics have been doing this for ages, right? If you want to estimate what's going to be the outcome in the next election, then you sample a small amount of people, definitely not the entire population, and you get a reasonably good estimate, usually. But the question is, can we apply the same approach to algorithms? And so what's the problem? The problem is in algorithms, we're trying to understand much more intricate properties of our data, not just counting how many people voted this or that. We want to understand relations and how do things relate to, and how do things build on top of each other. So really, the challenge here is try to apply the same idea of looking on a small sample and apply it to more general algorithmic problems. So this approach was suggested, it's not new, it was suggested 20 or 30 years ago, but we have been developing more and more tools to rigorously prove that those things actually work in more and more complicated settings. And today I decided to talk about just one area, just for the lack of time, which is that of local proofs, but I want to mention that ideas for local algorithms seem to be very promising also in dynamic programming type of situations, like when you're doing in biology, when you want to match patterns, which you have huge amounts of data sets that you want to match them to each other, which seems to be inherently non-local. There are some local approaches in coding theory, in some analysis of networks, and so on. But I want to focus on just one area to illustrate the main ideas. So if you've ever read a mathematical paper or anything that's trying to prove something, you know that the proof is something that's very non-local. You can have a very long proof for something with one mistake, and this one mistake can destroy everything. So it seems that intuitively things like a proof, things that are very combinatorial, very complex, are also very non-local, that there is no way of making them to be very, very, so that we can validate them with just looking at a few parts of the proof. And it turns out that this intuition is actually false. So a big breakthrough in the theory of computer science in the 90s and 2000s was the development of what's called the PCP theorem. PCP stands for probabilistic checkable proofs, which essentially said that proofs can be made local. There is a way to build actually a very complex proof system that actually takes any proof in any language that you want and transform it into a language where it can be verified locally. So what do I mean by verified locally? So we have some encoded proof, and we have a verifier. So a verifier is somebody who's relatively weak, and I'm going to show you an application of it in a second, but it still wants to verify something about our claim. And this proof system has this property of being able to encode the proof in a way that if the statement is correct, you can make this encoded proof that the verifier will say, yeah, that's a good proof. But if the statement is false, then there is no encoded proof that would cheat the verifier. So let me give you two applications of this idea of local proofs. One comes when we have weak devices, like our mobile devices, who want to do some very fancy computation. So we don't have enough power then, so we want to delegate this to the cloud. Okay, so we're asking some question to the cloud. For example, can you translate some speech into text and so on? We get some answer, but what if we don't trust the cloud? So how can we verify that? Well, the cloud can in many cases give us some proof that what he did is correct. But how can we verify this proof? We're very weak. So one way to do it, which is one area of research that's active today, is to do it using these local proofs. And so the cloud will actually give some local proof so that our iPhone won't be fully convinced, but only 99.99% convinced that this is a correct proof, which is usually good enough for us. Somehow here in this approach, the main challenge is that all these theorems are proved in the theoretical setting where the constants are huge and there's too much blow up, and actually making them to work well in practice, it requires a lot of new ideas. Here's another type of application. This is one related more to theory. So it turns out that you can use local proofs also to give limitations on barriers on the capabilities of efficient computation. For example, you can use them to give barriers on how well you can approximate hard problems. So NP hard problems are problems that we are all very interested in. It's mainly also sort of a combinatorial optimization problem that are very interested in practice, but how hard it is to approximate them. We believe it's how to solve them, how hard it is to approximate this solution. And it turns out you can use the same machinery to show that you can't approximate too well. And here's the main idea. So let's say you had a problem. It could be approximated very well, and you encode it in such a proof. Well, in some sense, if you can almost solve it, you can in some way fool the verifier into thinking that you actually have a concrete proof, an actual proof of the problem. Well, then somehow the fact that this is a sound proof system means that you actually solve the problem, meaning that which we believe is hard. So this is again a very rough sketch of the idea, but the main idea that you can show that very good approximations can actually be transformed into full solutions to a problem without any approximation. So just to summarize, so I gave one specific application, but this entire area of local algorithm I think is very promising as an approach to handle huge amounts of data where we're doing very complex queries and processing on them, and now we want to get maybe some approximate solution, but doing it much more efficiently. Much more efficiently meaning if our input has gigabytes, we want to do it not even read it inside gigabytes or terabytes, just read a few kilobytes of it and still being able to get a good solution. Okay, thank you.